will be sharing the record with everyone afterwards. Alrighty. Hello, everyone. Welcome to CRISiSLab webinar 2024. I'm your host, Alicia Cui from CRISiSLab and also Joint Center for Disaster Research at Massey University. I'm a research officer focusing on communication and engagement. And we also have CRISiSLab team lead Associate Professor Raj Prasanna here today to facilitate the Q&A session later. This is our very first webinar this year. We're very glad to have invited Dr. Jan Andrews from GNS Science to present on experiments in earthquake early warning transplantation. For the first timers, welcome. So our CRISiSLab webinar has been happening since 2020, where we invite speakers from all over the world to share what's been done in the earthquake early warning space. So far, we had a number of researchers from Europe, America, and Asia to share the accomplishments and progress. And this time, let's hear about the work done by GNS, the leader of earth sciences in Aotearoa, New Zealand. So before we start, a bit of introduction about our speaker today. Dr. Jan Andrews is a seismologist at GNS Science. She has been working as part of the rapid characterization of earthquake and tsunami project, testing and operationalizing a suite of tools to improve the accuracy and timelessness of scientific response information. Having a PhD in deep earth seismology, she has worked in seismic monitoring and seismic algorithm development in a number of commercial and operational settings, most recently in Southern California as a staff seismologist at Caltech, an algorithm developer for the ShakeAlert earthquake early warning project. So Jan's research interests include rapid earthquake characterization methods for earthquake early warning and hazard response, algorithm development for real-time operations, delivery of earthquake information to end users, and regional and national seismic monitoring. She also has experience with media and public interaction in earthquake response. So today, the presentation will be touching on work undertaken by GNS Science in New Zealand and earthquake early warning work from ShakeAlert in the US. As usual, the presentation will be around 30 minutes and we will have Q&A afterwards. So feel free to put your questions in the chat box during the presentation if you have some burning ones, but also feel free to raise your hand afterwards during the Q&A session. Cool, without further ado, let's welcome Dr. Jan Andrews. I will be stopping sharing this, so Jan can share her slides.
Thank you, Alicia. Hopefully you can hear me okay. Great. So thank you for everyone coming today and thank you for the introduction. Thank you for the invitation. I absolutely love these CRISiSLab webinars. I've been attending for the last couple of years and it's such a great community to be part of and such a great program. So thank you very much for the opportunity. My presentation is experiments in earthquake early warning transplantation, and obviously that's mainly a reference to some of the technological challenges of taking these methods from one place to another, but also a slight allusion to myself. I am a transplant, a Brit originally, and obviously arrived here in New Zealand via America, so on my own world tour as well. These kinds of earthquake early warning projects are big collaborations. And so I'm trying to acknowledge on this title slide here all the many different people at the different institutions that I've had the privilege to work with on these projects. And there's too many names to list them all out. So I just want to do a quick shout out to Maren Berzer, who is the originator of the Finder algorithm that I'll be talking about a lot. She's at ETH Zurich. And I want to acknowledge working closely with her for the last 6 years on a lot of the things I'll be presenting today, and also my colleagues here at GNS within the RCET program. So Yannick, Anna and Bill, who've also worked on a lot of this project. So diving in, this is a brief outline of the talk. So I'm going to start out with some framing context for the challenges for earthquake early warning, for moving these methods from one place to another in the context of the global EEW systems and algorithms. And then most of my talk will be specifically on Finder and our experiences here in New Zealand in configuring and what performance we've seen for it and its potential for delivering EEW here in the country, and wrap up with some summary and future directions. So I'll start out. This is a slide. So this figure is taken from the paper from Richard Allen and Stogaitis. They're working on the Android Google alerts. And the point really was to show some of the different countries around the world where operational systems for earthquake early warning exist. And this is already 2 years out of date. And since then, we have seen an acceleration in sort of the operationalization of these kinds of systems, either fully public or in prototype. And so I think it's fair to ask, and it's a question that arises a lot, of why can't we just sort of pick up these systems that have been deployed elsewhere and put them into any new context? So on the right, I've tried to list out what I see as some of the challenges when you're transplanting these technologies. Obviously, there's the tectonic setting. Every place is different. New Zealand is especially complex. And so adapting these methodologies requires some work there. There's also the technological environment. We're dealing with different sensor, communication, power systems, alert networks, all of that. The third one, social environment, obviously hugely important. There can be different expectations on these EEW systems, different levels of education and outreach that are needed. And we often talk about the difference in behavioral response, sort of compliant behavior between different societies. And then finally, of course, the big challenge of different economic and political environments, whether that's the amount of resource that a society and a community can put into one of these systems, or something like whether a national alert infrastructure exists and what that capability is. So diving into some of the more of the details, this is the cartoon that we have when we start talking about earthquake early warning, and we start to tell this wonderfully clear story about what earthquake early warning technologies are. So we have an earthquake, it's started to occur, we're trying to detect and characterize that as rapidly as possible. And then because we can transmit messages faster than seismic waves can travel, we're hoping that we can deliver with some meaningful warning time an alert to a vulnerable population before strong shaking arrives. But we all know that this sort of simple cartoon, and I've borrowed this one from the ShakeAlert system, belies a lot of the complexity and the differences that exist in these EEW systems around the world. So once we start peeking under the hood, we see that no two systems are the same, and they come in lots of different shapes and sizes. And to demonstrate that, I've just picked out these 3 overview diagrams from different systems around the world that have been published. So on the top here is Japan, and then we've got USA on the bottom left and China on the bottom right. And I think you can see from the number of boxes and arrows that are on here that these are complicated multi-component systems, and pretty much all of them are hybrids in terms of the sensors and the algorithms that go in them. And that's true for very good reasons. These systems, they're trying to be as effective and optimized as possible. And these systems are also relatively new, especially in the context of our earthquake recurrence periods. So fortunately, these systems haven't seen that many great and very damaging earthquakes. And so every time something does happen, whether that's a moderate or a very large earthquake, the people who are running and developing these systems are learning new things, trying to further optimize the system, further develop the system. And part of that is everybody learning from each other. So a lot of this transplantation is happening around the world right now. So taking components that have developed in one place and putting them elsewhere. So just as an example, the Plum algorithm that was developed in Japan is being tested and optimized for use in the USA as part of the ShakeAlert system. And equally, the Finder algorithm, which I'm going to talk about a lot in the rest of this presentation, is being tested and developed for use in China. So a lot of this sort of sharing of information and testing in new environments. So before I dive into Finder specifically, I just wanted to talk a bit about why there's so much complexity in these systems, why we run different algorithms, what these different technologies are. And it's because they have complementary strengths and weaknesses. So that's why these systems have tended to pick up a number of different methods to try and make them more robust and more effective in more scenarios. And earthquake early warning algorithms come in these sort of main three flavors. The first over on the left here is the point source algorithms. They're probably the most familiar for anyone that's worked in or knows much about seismic monitoring. The idea is to very rapidly characterize the epicenter or hypercenter and magnitude, so treating this earthquake as a point on a map. And from there, the source characteristics are used to estimate ground motion. So that's that picture on the bottom of a classic point on a map for the earthquake ground motion estimates. The middle group are the finite faults. So this is starting to recognize that for the largest earthquakes, a point is an insufficient representation of an earthquake. It's extended in space and time. So they're trying to characterize the rupture extent, maybe even the slip distribution along that fault, and from there go on to compute ground motion with slightly more complexity. So as you can see on the bottom there for the Finder example. And then on the right-hand side, the ground motion algorithms, they're throwing away the source completely, and we don't worry about characterizing it. We're just going to propagate ground motion. So based on our existing ground motion observations, propagating those out to an estimate of future ground motion. On the bottom row, there are a number of different algorithms that you can see within each of these categories. And as I say, they have different strengths and weaknesses. So the point source ones tend to be the fastest, but they have magnitude saturation, and so they can't be used for the very largest earthquakes. They tend to underestimate both magnitude and ground motion. Those finite fault methods tend to be a little bit slower, but they don't have those saturation issues. And then our ground motion ones, they offer us a lot of speed and sort of sensitivity in terms of ground motion estimations, but they tend to have limited warning times because of the methodology. So again, different strengths and weaknesses here. So diving into Finder specifically, it's, as I've mentioned, is part of the ShakeAlert earthquake early warning system, and it's one of these methods that attempts to characterize the extended finite fault. It started off actually in development in Turkey as part of Maren Böz's PhD, and it's been implemented in Switzerland as part of their prototype system and in Central America as part of their operational system starting last year. And it's further being tested now, as I mentioned, for China, in Taiwan, in Canada, and by us here in New Zealand. And what does it look like? So Finder stands for the Finite Fault Rupture Detector, and it's a relatively simple method. So that's shown on the diagram here. So if we start with our observations in the middle, we're taking in point observations, so seismic station observations of peak ground acceleration. So that's high frequency, high amplitude ground motions. That gets turned into a ground motion map. So it's interpolated. We apply a PGA threshold to turn that into a binary image. And that spatial kernel of high frequency, high amplitude ground motion is compared against a pre-computed catalog of templates to find the best matching rupture estimates. So our output information are rupture location, rupture extent, which can be turned into a magnitude using a scaling relation, rupture orientation. And because we get a series of snapshots through time, we get rupture directivity. And because we have location and extent here in New Zealand, it's quite important. It can help us to assess the possibility of coastal or offshore rupture and any potential tsunami hazard that arises from that. So when we started to bring Finder into New Zealand, there were a couple of configuration parameters that we need to tune or to tweak or to look at to optimize performance here. And the first set of parameters are for detection. So Finder doesn't rely on anything else to detect an earthquake. It's doing that itself based on the raw data input it receives. And so things like network topology, so network station spacing and station heterogeneity, and the noise across the network are quite important to consider so that we get the best performance. And the other are those pre-computed ground motion templates, which can be made region specific to try and improve local performance. So you want to consider local tectonic seismic sources, local ground motion relations, and the site conditions across the network. So here in New Zealand, we're running with two different classes of ground motion templates. They're computed using the ShakeMap software. One is for crustal strike slip earthquakes, as demonstrated by the figure on the the left there, that's using crustal scaling relations and ground motion prediction equations and characteristic earthquake parameters. And then on the right is an example of the subduction interface templates using those interface relations. And in the middle is just a comparison. You can see that they differ there in their ground motion characteristics. So once we've got our configuration set up, we want to start testing the system to try and understand what performance we might be able to expect once we start running in real time. So one of the things we did here in New Zealand was to create a series of synthetic sources around New Zealand for different magnitude events and see what impact the network distribution, so the network density and heterogeneity, might have on our ability to characterize the rupture successfully. And so these figures, if we look at the middle panel, this is how well we recover things like magnitude and location for magnitude 6.5 or 7.5 earthquakes that occur onshore New Zealand. And you can see from the top panels, those yellowy colors are showing that we do a pretty good job of recovering magnitude. For location, we do, again, pretty well for these onshore events. Unless for the larger magnitude events, we start to extend offshore and then find it struggles to see that offshore extension for these earthquakes. And then in terms of strike or orientation of these ruptures, that's really to do with the station spacing versus the spatial extent of the earthquake. So you can see for magnitude 6.5 onshore, we start to do slightly less well where the station network is more sparse. But in general, we can expect pretty good behavior, except for some of the more challenging regions up in the north of New Zealand. For onshore events, once we start to move offshore, it gets a lot harder. Finder's methodology is based on being able to well characterize epicentral ground motions. And so as we move offshore and that isn't captured, it degrades our performance. So you can see that in the top panel, we do a reasonable job up to about 50, 75 kilometers offshore of getting a magnitude estimate, but locations start to be degraded. Finder tends to pull those locations onshore and into the network, and we don't recover strike very well. So good for us to know as we move into real-time testing. The next tests that we were running are for historic earthquakes. So we have taken the 3 largest recent earthquakes, the magnitude 7s, and started to replay those through our Finder system. And if I can start this, video going. So this is an animation of Finder performance during that replay for the 2016 magnitude 7.8 Kaikoura event. And Finder performs really well for this earthquake, this very large extended source. So it starts to make its first detection after about 7 seconds with a magnitude 4.3. And then the solutions that Finder outputs evolve in real time as that rupture evolves until it gives us this final estimate of magnitude 7.6, about 100 seconds after origin. And as you can see from the middle panel here, which compares Finder's last estimate in pink against the mapped ruptures and also the aftershocks from Callum Chamberlain's catalogue, Finder does a really good job at a sort of quick and dirty estimate of this rupture extent and location. It's not designed to be hugely accurate, but this is a huge step forward in terms of the situational awareness information we have, given that it's with us in a couple of minutes after earthquake origin. And over on the left-hand side is a sort of still of that time series of centroids. And the other information it can give us, obviously, is this directivity. So it's clear that this rupture was propagating up to the northeast. If we take this then to Darfield, which is a more, it's a magnitude 7.1 in 2010. This again occurred in a dense area of the network. So we make Finder is able to make a very rapid first detection with an estimate after just a few seconds of a magnitude 3.6. And that's evolving in real time then with the rupture for a final estimate of magnitude 7 about 40 seconds after origin. Again, comparing the final rupture estimate from Finder against the aftershock catalogue compiled by Stephen Bannister. That's a really good correlation. And the still of the time series on the left-hand side there shows that it's also capturing that rupture towards the east. moving on to the third big event that we tested, the magnitude 7.8 dusky sound event from 2009. This is a much more challenging scenario for Finder. This event nucleated right on the southwestern corner of the South Island, so pretty much on the edge of the network, if not just outside it. And then it actually propagated away from the network down to the southwest. So really, really difficult for Finder to do a good job here. You'll notice that it took a lot longer for the first estimate, nearly 20 seconds because of the sparse station density here. And while the magnitude estimates do evolve up to a 6.6, it in no way captures that full magnitude 7.8. And you can see from the central panel that the location estimate error is poor as well. So a really challenging scenario for Finder, and it's good for us to know at this point what we can and can't expect from the method as we start running in real time. So that brings me on to the real-time testing. We've had Finder up and running here in New Zealand for about 14 months now, since late January of last year. And in that time period, we've detected 57 events with the system, and that's shown with the map here on the right-hand side. All of these coloured circles are the events that were successfully detected. And then we've got a few coloured crosses that are showing missed events, and the black crosses, which are false detections. So focusing in just on the successful detections, they range in catalogue magnitude from about 2.9, and we only get that sort of sensitivity in very dense network areas like the Canterbury region or the Wellington region. And we've captured a few magnitude 6s. I think we've had about 3 over this time period. Detection times can be as fast as about 7 seconds, again, in those dense network areas, and up to 100 seconds. And those very long detection times are usually because of deep slab events. So that travel time up to the surface is a big component of the delay. We do a pretty good job of estimating magnitude and location. There's a slight tendency to underestimate magnitudes, but that's partly to do with the parameters we're using to create templates, and partly to do with the local versus moment magnitude discrepancy we have here in our GNet catalogue. In terms of missed and false events, this is less of a concern for our rapid rupture characterization question, but still interesting to look at sort of the sensitivity of Finder here in New Zealand. So in terms of missed events, we've missed for crustal, so shallower than 40 kilometres, we've missed about 12 catalogue events of magnitude 4.5 and above, and just 1 magnitude 5. And if we look at those in the map view, the magnitude 5 is this one over here at the Chatham Rise. So fair enough, we're not expecting to be able to see anything that far offshore. Same for some of those East Cape events. And really, even for the onshore ones, they're at the limit of detection given the station density in these places. So really not of any concern for us. The one interesting one, to me at least, was the one up in the Kawerau region, which was a magnitude 4.7. And it really starts to highlight that the attenuation of the high frequency ground motions in our geothermal and volcanic regions here in New Zealand really modify our magnitude sensitivity. So an interesting thing just to keep in mind for us. And then in terms of false events, and these are false events that are triggered purely on noise across the network. We've seen about 5 where Finder came up with a magnitude of 4.5 or greater solution, and 1 of magnitude 5. So I'll talk about those in a couple of slides in more detail. But just to give an example of what these Finder solutions look like for the response scientists here at GNS in RCET that received them. This is an example for the Methven event that was just a couple of weeks ago. It's a catalogue magnitude 5.1, local magnitude, moment magnitude 4.5. So we see a really nice waveform view here. There's a picture of the PGA values and the Finder epicenter. And on the bottom middle panel, this is the different Finder centroids through time, and I've dropped in the catalogue centroid so you can see the location error is pretty good given our sensitivity. So it was detected in 13 seconds, which is great. It's not the densest part of the network here. And the magnitude estimate is in good agreement, at least with the moment magnitude, so around 4.5. But if we start to drill down to where the performance is a bit more challenging, this is a view of some of the false events. I mentioned a few slides ago that some of the configuration parameters we can tweak is how Finder decides it's detected an earthquake. And we have the configuration here that we require 4 stations to exceed a PGA of 2 centimeters per second squared. And then we do some spatial and temporal coherence checks as well. And that's fairly conservative for an earthquake early warning algorithm, which can typically use just 2 or 3 sensors to determine if an event is happening. But even so, we get we've had around 20 false nucleations of magnitude 4 and above in the 14 months we've been running. And while this isn't really a concern to us from a rapid rupture characterization point of view, or even from early warning, because a lot of these, it's quite easy for us to tell that they're false, and we wouldn't necessarily push out an alert even to our response scientists. It's interesting for comparison to ShakeAlert, where in a 4-year period, we saw no false detections of magnitude 4 plus and above. So this is really speaking to the fact that we need to understand and tune for the noise characteristics of our local network. The other interesting observation when we've been watching Finder work in real time here in New Zealand are these grossly mislocated events. And this is because of the subduction zone environment, the strong slab-guided waves that we get here in New Zealand. So these are just 2 examples I picked out. They have very large location areas. So if you look at the example on the left here, this is for a slab event 170 kilometers deep in the Bay of Plenty. You can see that the stations with peak ground motions were actually those Gisborne stations. And so what Finder did what Finder is supposed to do, which is to locate an event where it sees high ground motion. So it puts its epicenter offshore East Cape, so a few hundred kilometers of difference to the true epicenter. And then the event over on the right, this was in sort of east side of the North Island. And you might be able to see, so the panels show the shape maps for these events. But again, the highest ground motion was for these stations down in the center at, sorry. I don't know how I get back to display mode. Sorry, bear with me.
That's all right. Well, Jane is finding back her slides. Maybe the rest of you can think about what questions and you want to ask later on and put them in the chat box. So far, it's been very interesting, so looking forward to more.
Oh dear. Let's see if we can.
Now we can see your first slide. Here you go.
Okay, hopefully we can see we're back with these mislocated events. And so, yeah, you can see that we end up with a Finder is doing what it's supposed to do. It's recognizing the high amplitude ground motion stations, putting the epicenter there, but it's this big location error in terms of the epicenters. However, in terms of if we looked forwards towards whether this is earthquake early warning, it is a great question as to whether this is actually bad behavior or not, since it's more to do with impact in EEW than it is about source characterization. So I've talked a lot about some of the challenges of transplanting Finder specifically, and I wanted to make the point that it isn't a Finder specific problem, that other algorithms, as they've been taken from one tectonic setting to another, have faced similar challenges. So I can't speak to all of this slide, but this is an example for a point source algorithm, EPIC. It was developed in California for the ShakeAlert system, but it was taken to Israel to be part of their prototype EEW system. And the authors note in their study that it was highly customized to that California environment and to the local networks, and that work needed to be done for things like characteristic earthquake parameters and velocity models in order to make it work effectively. If we look at another scenario, which is taking plum from the Japan setting to the US, again, Elizabeth Cochrane and her co-authors noted that several modifications were necessary to account for different station distributions and differences in alerting. So these figures just quickly show that in Japan, the plum system there, they've got two key advantages. One is that they're applying real-time ground motion corrections to their stations. And the second is that they have this prefecture-based alerting system. So when it moved to California, not only have they had to, or to the US, not only have they had to play around with configurations to try and optimize it, but they're even looking to modify the method to make it perform better within the ShakeAlert setting. So this slide is speaking to a study that came out this year from Jessie Saunders and her co-authors, which is showing that when trying to use plum in the US setting, they were struggling with over-alerting. So this is too wide a region being warned during earthquake early warning events. And so they're looking at applying attenuation to the plum algorithm to reduce that over-alerting problem. And this is partly because they don't have these real-time corrections to the station observations, and partly because it's a polygon alerting strategy rather than a prefecture alerting strategy. So again, all these challenges to taking methods from one place to another. Stepping back to Finder, not only have we been playing around with sort of configuring or optimizing for different settings as it's been moved around, but also can we do a better job if we highly regionalize the configuration? So this is some work that we've been doing to rather step away from using generic ground motion templates and see if we can use fault-specific or scenario-specific ground motion templates to improve our future ground motion estimates, so our ground motion estimates for alerting. And these are just some examples. So on the left-hand side is an example for the Cascadia subduction zone. So moving from just a simple line representation of the source to now rupture patches on a subduction interface. And we've been testing that using synthetic magnitude 9 synthetics from Frankel and Wirth. And on the right is an example of trying to bring in the complexity of the San Andreas ruptures, the different geometry there, and testing that with the shakeout scenario from Graves et al. So again, sort of trying to take the next steps to improve ground motion estimates. And in some recent work in a paper that should come out this in a couple of months, taking this and then applying it to the devastating Turkey-Syria sequence from February of last year. You can see in these panels on the left, these black lines now are faults in the active fault database for Turkey. So we've created scenarios, fault-specific templates for these different fault traces, and then running forwards with the data for the magnitude 7.8 Pazarchik or the magnitude 7.6 Elbastan earthquake on the bottom there, and seeing what Finder recovers now in terms of these more scenario-specific or fault geometry-specific solutions. And to take that even one step further, we've been looking into projecting slip now. So rather than just recovering a fault extent or a rupture extent, but projecting slip based on the peak ground displacement observations onto these rupture extents to see if we can isolate where regions of particularly high slip are, which again have implications for the ground motion estimates and impact. As a final note on synthetic testing, I wanted to make the point that these earthquake early warning systems are they're relatively new, as I said, in terms of a recurrence of these very great, very damaging earthquakes. And one of the challenges, of course, is that we want to make these systems as robust and as optimized as possible, but we have very limited data to work with. So one of the challenges is coming up with lots and lots of different synthetic scenarios to test these systems to ensure that they will be reliable. And this is a piece of work that, again, Maren led, that we worked on while we were at ShakeAlert to test Finder specifically in this case, the results I'm showing here, sorry, with not only large magnitude earthquakes, but other challenging scenarios like foreshock, main shock, aftershock sequences, or triggered seismicity, or events where, say, stations in the epicentral region have been degraded or compromised because of previous events in a sequence, and seeing how the algorithm performs. But we're going to switch gears now. So this is the next piece of work I'm going to describe is about testing Finder's potential to deliver earthquake early warning here in New Zealand using the GNS network. So now that we have the system up and running and we know it offers some benefit for rupture characterization, the idea was to take a suite of magnitude 6 and 7 events from the historic catalogue and see, well, if the system was running, could it deliver any kind of useful warning with the system that we currently have, with the sensor network that we currently have. So in order to do that, we need to define some earthquake early warning metrics. What does success look like for us here? So this slide is to show the metrics of Menandrin Meyer that he published in 2017. And this is what I've computed in this study. So if you look at the picture on the top left, what we're doing now is taking every sensor in our network and treating it as a site to be potentially alerted. So on the x-axis is time, on the y-axis is intensity. The coloured line, the line with different colours is our observed MMI at the site. So we've got the P arrival coming in and then the peak amplitude evolving as the S wave and surface waves arrive. The red line is the predicted intensity for this site. So the yellow star that's our origin time. A few seconds later, our first detection comes in and our first prediction for this site. And that's again evolving through time as our algorithm evolves through time. Once we have this observation and prediction, we can apply a threshold, say this is when we're going to actually start alerting this site, and we can come up with the warning time, and we can compare observed and predicted intensities. It gets a little bit more complicated if you look at the figure just below that. This is the idea that because ground motion prediction is difficult to predict, and there's a lot of uncertainty, that we actually start alerting at a slightly lower threshold than we're truly interested in, just to make sure we can offer longer warning times and capture more sites. And so we have a separation between the threshold of interest and our threshold of first alerting. But once we've computed these metrics for the sites, we can start grouping them, we can start characterizing them. So that's captured by the boxes on the left. So now any site that's coloured in blue has been offered a timely warning with some positive warning site, and it's a sort of correct alert. Anything in yellow was also alerted in a timely way. The ground motion just didn't reach that damaging threshold, but it was probably felt. Anything in black, we were probably too late. It was too close to the source. Anything in orange, those are our false positive sites. So that's when we alerted it, but the ground motion didn't reach that felt threshold. And anything in red, we didn't alert, but it did have potentially damaging shaking, felt shaking. The only other step we need to do in order to complete this study is to turn our Finder solutions now into earthquake early warning alerts. And so I've done that with a simple polygon alerting strategy. So here, just taking the Finder solution, determined a radius from our ground motion prediction and ground motion intensity conversion equations to turn that into a polygon. And because we have a time series, so the figure on the bottom right, we just have a time series of alert polygons now. And then, of course, I've had to apply some thresholds. So here we're going to alert whenever the magnitude exceeds 4.5. Our shaking threshold of interest is potentially damaging at MMI 5, but we're going to start alerting at felt MMI 3.5. So if we compute those statistics for a replay of the Kaikoura magnitude 7.8, this event should offer us the best opportunity to do a good job for earthquake early warning. There's a large impacted region, and as we know, Finder was able to do a pretty good job at characterizing the rupture, as you can see in the top right. And that's played out. If you look at the center panel in the bottom row here, this is observed against predicted MMI, and you can see that falls really nicely on the equality line, but with a lot of scatter because of that challenge of predicting ground motion accurately. In terms of the warning times, there's a high percentage of correctly warned sites in this case. So if you look at the figure on the bottom right, this is now warning time against the empirical CDF, so the percentage of sites correctly warned and with what warning time. The warning times here go from about 2 minutes to a second. For the very highly damaged sites, so MMI 8+ sites, still over half of those sites are being alerted with positive warning times, and up to 100% of sites with potentially damaging shaking, and with warning times that can reach up to a couple of minutes. But this picture is for zero latency in the system, and we know that it's going to take time for the data to come into our processing system and for an alert to be pushed out to any kind of stakeholders or public. So if we allow for about 10 seconds on that, which is fairly conservative, but could be that long, especially for things like cell phone alerting, you can see that there's a reduction in the percentage of sites alerted and a reduction in the potential warning time that can be given. But there's still a high percentage of sites that could be given positive warning times of 10 seconds and up to minutes. It's a much harder picture for an event like Darfield, the magnitude 7.2, partly because a lot of the sites are now in the Christchurch area, so very, very close to that epicentral region. And it's also a much smaller event, so a smaller impacted area. But there's still some 50% of sites that could be with potentially damaging shaking that could be warned with up to tens of seconds of positive warning time. But if we then account for that 10 seconds of potential latency in the system, that drops down to maybe only sort of 40% of sites giving some few seconds to tens of seconds of warning. But there's still a potential for good to be done. If we look at the even harder category of the magnitude 6 to 7 events, this is just a study with four events from the historic catalogue: Christchurch, Eketahuna, Cook Strait and Lake Grasmere. And this problem gets harder for two reasons. One is that Finder is now going to struggle more to characterise the source because we have a smaller source extent, and some of these are in quite sparse station areas. And we also have that problem of a smaller impacted region. So we're going to have to work a lot harder to provide warnings to impacted sites, strongly impacted sites. And you can see that from the figures on the top, that Finder isn't necessarily doing a brilliant job at characterising the source. You can also see that in that middle row where we're not falling as neatly on the equality line between observed and predicted MMIs. But from an early warning perspective, we're not actually too hampered by that ground motion accuracy because speed is the most important thing for us. So we can still do a reasonable job there, even without very good source characterization. If we look at warning times on the bottom, in this case, we can still offer sort of a few to maybe tens of seconds to sites that should receive potentially damaging MMI 5 shaking. But if we start to introduce latency into that, that's going to drop down to maybe just 50% of sites could receive maybe a few seconds of warning that damaging shaking is coming. I'll skip through this because I know I'm running long on time. So I'll summarize here. So what I've tried to describe is some of the challenges, the general challenges for transplanting these earthquake early warning methods from one place to another. I think it's really important to understand the underlying factors that are going to impact the system. That includes the instrumentation that you're working with, whether that's things like changes in station density or in noise characteristics across the network. Also the tectonics, so the seismic characteristics, things like different depths to events, waveguide effects, and also your algorithm configuration, which parameters need to be tuned and can be tuned to your setting. I think it's really important to build up a test data set with as much region-specific data that you can get your hands on, both for historic scenarios and expected scenarios or unexpected scenarios. So what those worst cases might look at in order to design and determine a robust system. I also think it's really important to understand your target system performance. So what are the expectations? What are the needs of end users and stakeholders in order for these warnings to be useful and effective? In terms of our experience in testing Finder here in New Zealand, I think we're seeing that there is huge value for rapid rupture characterization. So in that response context of situational awareness and response decision making. But we're still working, there's still work to do in terms of optimizing and testing, especially for the offshore setting. I think that last study has shown that And this was a surprise to me, actually, that there is promise for earthquake early warning, even with the existing GNet network and national network infrastructure. But there's still more work to be done in terms of desired behavior and societal expectation and all of that, those pieces that are involved in alert delivery. In terms of future work, I'd really like to start working with the RSQ sim synthetics for different large magnitude scenarios. Fortunately, we don't have very many in the historic catalogue, and we need more to be able to test the system. I'm really interested in integrating with the low-cost sensor networks, such as those that the CRISiSLab folks are working with, and seeing what that can offer, and also trying out with felt reports as well as a different data stream into an algorithm like Finder. And then finally, Finder is just one EEW algorithm, so looking at some of the other algorithms that are out there and what they might be able to achieve in New Zealand. And with that, thank you very much. Happy to take questions.
Thank you so much, Jen. And that was an awesome presentation. You have kind of delivered it in a kind of a easy to understand way. So not being a seismologist, I mean, it's great to hear some of these comparisons. So thinking about the timing, so we'll straight away, I think, jump into the questions. So in the chat box, we have one question. Probably we'll start with that. And yeah, it would be great others put something here or put your hands up and ask the question. So the first one is from Chantuchen. Do you think the number of stations in New Zealand is enough to implement a successful EW system with the Find algorithm?
That is a great question. And I would say possibly in some places, definitely not everywhere. So the average detection time that we're seeing for, say, the Canterbury region or the Wellington region is around 7 seconds, which is comparable to EEW systems elsewhere in the world. And so if we had events in proximity to those sort of very dense parts of the network, there's a potential for effective EEW. But I think it'd be nice to do a sort of targeted study on the network density to see where we could or couldn't offer meaningful warning times, and really try and target it to where you would need to densify the network here in New Zealand relative to a vulnerable population. So if you look at earthquake early warning systems in other countries like Japan or the US, they've adopted this policy of just saying, well, we want 10-kilometer spacing or 20-kilometer spacing. I think it would benefit New Zealand to be a bit more targeted, because we do have a fairly sparse population, and really consider where do we need the network to be dense, considering where our population is and where our seismic sources are. So sorry, a bit of a long and rambly answer, but a combination of yes and no.
Thanks, Jen. That's great. So the next one we have from Tim. Is the current communication latency of the GeoNet network sufficient for operating Finder in a real-time environment? I mean, probably that has linked to the station density as well.
Yeah, another great question, Tim. And it depends on what you mean by operating Finder in a real-time environment. So obviously we are operating, and we're operating it as a rapid rupture characterization, and for that we're all good. In terms of delivering earthquake early warning, there's a lot of easy wins to be gained from optimizing the GNet communications latency, I think. I think Rasika, who is online and can correct me, found that the average latency is about 4 seconds in the GNet network. And that's longer than, say, the ShakeAlert network, where I think most station latencies are down at sort of 1 to 2 seconds. And that's just to do with data logger configurations and so on. So I think it'd be easy wins to gain a few seconds there. But again, there are probably places where even with the existing setup, you could have some effective earthquake early warnings, but it always helps to shave off those seconds to improve your warning times.
Cool. Okay, before we go into the next ones, I have a question. Probably I'll ask that related to earlier questions as well. So thinking that all these algorithms have positives and negatives or challenges, do you think there's a hybrid way forward for a country like us here if we go with these kind of earthquake early warning applications in the future, Jane?
Yeah, I mean, obviously other countries have decided that running multiple algorithms is the way to go to optimize. And I like that. It brings its own challenges because you then need to do some decision making between what final alerts you're going to send out. I think it's worth testing a number in New Zealand just to see what best fits the operation and requirements here, you know, in terms of the network, in terms of the population, to find the best way forwards. But it's great that all of these different options do exist around the world and can be tested. So we can leverage that.
Well, and then we have a question from Quincy. It's related to intellectual property issues when considering transplanting EW from overseas to New Zealand. And who do you think is the most promising internationally alive for EW in New Zealand? It's a great question.
I'm not sure I can answer that last one. I would like to say that the international EEW community is an incredibly great sort of collaborative environment. And when it comes to things like intellectual property, like pretty much everything is open source and widely shared. So there's a lot of exchange in that community and a lot of goodwill and a willingness to learn from each other. So I think if possible, we should, you know, collaborate with as many as we can. And I know there are strong links already with Europe and the US and Canada and so on.
Cool. Then, yeah, Alicia had a question, just wondering what kind of engagement work has been done regarding the community's attitude towards EW done by GNS.
So GNS, there's a number of different groups, right? I know at Massey, Julia Becker and Lauren Vanell and others have done a lot of engagement work. At GNS, Sally Potter has been involved in a number of outreach efforts or social science studies for earthquake early warning as well. But I think there's still a lot to do, and certainly for us on the technical side, there's still a lot of work to do, engaging with stakeholders to understand things like technical applications, requirements on warning times or ground motion accuracy, for example, for different technical actions to be taken. I think there's still a lot to be done there.
And Peter Wood has a question about how we are kind of connecting this to tsunami warnings. We are long, I mean, he's thinking that are we long away from local tsunami warnings? And what do you think is needed to improve local tsunami warnings?
That is a big question. And yes, I agree. For a local earthquake source, we're still a long way from offering tsunami warnings. And that's both a scientific challenge and a technical challenge in terms of our alert pathways. And I think actually on that alert pathways, that's something that we haven't attempted to tackle. So I talked about, 10 seconds to go from our automated systems to push out to the public. We do not have a pipeline that can achieve that at the moment. If you think about tsunami warnings, there's a lot of actual manual action that needs to happen in terms of transferring information from one system to another and pushing that out to the public. So there's certainly a lot that could be done in terms of integrating that system or smoothing out the friction in that system that might help us to shave time off in delivering those warnings.
Well, that's great, thanks. And then also Rasika has a question. Does the finder consider stations, 4 GeoNet stations, for example, within a certain range? And does a timeout of 90 seconds imply that it assumes there are no other events happening within that time?
So the distance range, which I think is what you mean by certain range, that is, it does a real-time calculation of what its nearest neighbours are based on the data it's receiving. And so they have to be neighbouring stations allowing some kind of tolerance. So sort of 4 within 8 of its neighbours have to trigger. It's that kind of spatial coherence check that it does. The 90-second time window, it doesn't imply that no other events are happening. It can handle multiple simultaneous events, but of course, it's just based on an amplitude threshold. So if you're saturated with energy from one event, you wouldn't be able to pick up an aftershock, for example, because it holds that peak amplitude in a time buffer for a certain amount of time afterwards. So there are issues with aftershock detection, certainly. Yeah.
Thanks. Yeah, so this is something related to latency and processing. So this is question from Derek. Is the location of the processing center important? That is, if it is closer to seismically active area, does it risk being damaged before it can do its processing? Or if it is far from seismically active area, it reduces risk but adds latency?
So there isn't something that we've considered, I think, for New Zealand at this point, because we're just working with sort of prototype and test systems within RCET. We only have the GNS processing at the moment. But for a system like ShakeAlert, that's definitely a consideration. They operate 4 redundant computation sites in Southern California, Northern California, Seattle, and up in Canada now. For exactly that reason, all of the information is exchanged. The idea is you've got high redundancy so that if one center fails, the others will still be issuing alerts. In terms of adding latency, it's not significant. I think it's only tiny fractions of a second. So redundancy will always be a good thing to mitigate that problem.
Thanks, Jen. Alicia, can we take a couple of questions? Yeah, is that okay? Okay, cool. Yeah, and then Uma has got a question. Thanks, Jen. Would find algorithm can suggest optimum number of monitoring sensors for a region of interest?
Yeah, so definitely it's possible to run these kind of optimization algorithms to understand what's the ideal configuration for an algorithm and a region. So they've done something similar for Europe, where they've, tried to decide where it would be best to add in sensors to optimize performance. I think the challenge for us in New Zealand and as an early warning community is that you don't want to be too targeted. As you mentioned, Raj, it's great to explore different algorithms, and we really want to design a system that's going to be future-proof against new algorithms coming in, new technologies coming in, and to make sure that we're not too specifically tuned and locked into one method. We want to be a bit more agile than that, but certainly we can do those kinds of optimizations.
Cool. And there's more of a comment from David. USGS source code and algorithms are required to be in the public domain. So do you have anything to add to that, Jen?
No, just that I think it's a great aspect of the collaboration, and I certainly appreciate the ShakeMap software.
Yeah, and then there's a question from Keith. Have you investigated the Taiwanese CW system using the so they are PAlert and hybrid thing? We at GenLogix have been successfully providing our private and commercial clients with on-site EW for several years now, and then more recently in Jakarta for a new light rail system. So any comments around that, Shane?
That I think there's a great opportunity for combined systems as well. I mean, on-site systems, are demonstrated and are used around the world. And I think it's more about, understanding the synergies between national network-based systems, on-site systems, trying to bring them all together so that you do get this maximum performance in terms of warning time and redundancy and robustness. And I think it's a great opportunity for us all to explore that.
Yeah, so probably I'll take one last question from my end. So we discussed about making the networks robust, and with these approaches, the amount of cost to maintain one sensor station, because we want to keep them going and communicate. And if one station is not available, how we can kind of keep the communication going. So do you feel that the mesh kind of approach or that decentralized approaches? What's your opinion about that, Chen?
I think it's Raj, it's very outside of my comfort zone. I'm very, very excited by the potential, especially that, as you say, the reliability, the redundancy that it offers. My fear as a scientist and wanting to be in control of it all are some of those challenges around understanding the network. As I mentioned, EEW algorithms tend to be very sensitive. They tend to require just a few sensors to trigger. And if you've got things coming online and offline, or maybe changing in noise characteristics, sort of having an algorithm that can cope with all that and being able to test for all that seems like a scientific challenge that we need to address. But in terms of, as you say, that sort of redundancy and agility of a system, I think it offers huge potential. A really interesting research area.
Thanks, Jen. Thanks so much for answering all we have a lot of questions, and that shows the interest. I think it's a great topic. And one thing from my end, I think great kind of clearly explained that we all can understand, although we are from different domains. So thank you so much. So I'll hand over to Alicia to kind of close the session.
Yeah, thank you very much, Jen. And thank you, Raj, for facilitating the questions. And thank you all for coming. And the recording will be uploaded to our YouTube channel afterwards and will be shared with all of you, and also to for who couldn't be here today. And see you in 2 months-ish. We will have another lineup, perhaps from Europe or South Korea, to talk about EU for us. Cool. Thank you for coming. See you next time.
See you, everyone. Thanks, Jen.
Thank you very much, Jen.
Yeah.